now that I have the coordinates of the focus and the equation of the directrix, okay, I can use that to try and get something about the eccentricity, a relationship. Now, last time we got this relationship, okay? Now, I just said a whole bunch of this stuff is the same, okay? So, some logic would say we're probably going to get the same relationship. How could you tell? How could you tell if it was the same? If it's not, then what is it? Do you remember how we did it? How did we get this relationship? We went back to the definition of what this thing is, right? We said it's PS on PD equals E. That's that, right? That's a distance formula. That's a perpendicular distance formula. Go. You can do it. It'll take you 90 seconds max. Go for it. I'll go stop this. Did you get there? Sorry, I'm in a bit of a hurry. Did you get there? Now, here's the part that's interesting to me. What did you have here underneath y squared?
A squared bracket E squared minus 2.
If you did your algebra right, that's what you should land on. Okay? Which is like, ooh, hold on. So much of this was the same. What went different? What is different? Can anyone see? How different is this to the ellipse that we looked at before? Think about what we started with. Look at these pieces. They're all the same. Okay? So what you've got in here, see, to make this an ellipse, you'd say, well, I need a plus there, don't I? Right? But if you get rid of one minus sign, it's got to go somewhere. So the most natural place is where this is. So that switches around, like so. Okay? So therefore, if we actually do want to stay with a hyperbola, right? You've got your minus there, but this is something which I think is easy to screw up. Okay, this is the trouble I had. You've learnt this for ellipses, but for hyperbola, it's the other way around. Okay, so please be careful. All right. Now, you did a good job getting the focus. That was fine. Getting the directrix, fine. Eccentricity, we can work out using this relationship here, namely that's b squared, isn't it? Right? So therefore, for hyperbola, we would write this: a squared e squared minus 1. Okay? So we can work out the eccentricity for this guy if we wanted to. Let's do it. What have I got here? B squared is 9 equals 25 e squared minus 1. Okay? 9 on 25. Add 1 gives you, what did that become? 34 on 25? Yeah? So e, we're taking the positive value because it's a ratio, so it's a square root of 34 on 5. What did do? Okay? Now, we haven't answered the question, what are a and b? What significance do they have to the hyperbola? Okay? We're pretty close with this. We already got this distance, right? So we noted that that was, what's it equal to? It's just 2a, right? Not much good to call it the major axis, but because it's a completely different geometric shape. So they give it a different name. This is not called the major axis. They call it, because it's going across between the two branches, they call it the transverse axis. Because it is still an axis of symmetry, that distance there from A to B across the x-axis. Okay. Now, what's the other piece? Where's B? Well, I already mentioned, right, that B has to do with, at least here, it had to do with your vertical squishing and squashing or stretching or whatever. Okay? It's doing exactly the same thing here. It's just that it doesn't do it on actual points, which is a little weird, I know. But it's still referring to a distance similar to this, but it's vertical. Okay? So it's going to be a distance like this. Now in this case, what do we have? This is just a made up one, was it? So if I had 9, okay, I'd have some points plus or minus 3, right? And that distance between them, I guess that would be 6, also gets given a name. It's called the conjugate axis. Okay? In some words, conjugate axis is kind of like a, like what does conjugate mean? We know, it just means the other one, doesn't it, right? It's like root 3 plus 2 and root 3 minus 2. Or a plus bi and a minus bi. It's just the other matching one, right? So I kind of view it as, it's the other axis, you know, this is the important one. Okay? However, we do get a very important phrase from this, okay? Let's take this idea, on 25, on 9. If I were to switch them, right? Literally swap them around, okay? I'm swapping the transverse axis and the conjugate axis. So we give that a name. I'll give you an example with this particular one I gave you before. If I said x squared on 9 and y squared on 25, okay? These guys are related to each other. They're the same thing, but they're rotated. No, sorry, not rotated. Their proportions are in reverse, okay? So we call it the conjugate axis. The conjugate hyperbola. Okay, because it's kind of like the matching one. Ooh, wait. No, what have I done? Other way around. Sorry. That should be y, and that should be x. So in fact, what you're going to get is, because when you switch x and y, what kind of geometric difference do you get? Like, what's the difference between this guy and this guy? It's 90 degrees, isn't it, right? So therefore, what you get when you rotate this 90 degrees is these guys. You see that? Okay. Now the important thing, because of the way the ratios work, and I'm going to double check this in a second, just to make sure I got it right, is that these conjugate hyperbole, they share the same asymptotes. You can almost even see it there, if I drew it properly. Anyway. So they have this special relationship to each other. Alright, one more special term to give to you while I'm talking about all these different weird names, and that is one which is sort of familiar because we've been drawing it for a long time. When you think about this guy, right? He's a bit different, isn't he? Because he doesn't have symmetry across the axes like that, or symmetry across these axes. He's off at an angle, okay? But the important thing about him is, well, let's just quickly draw it. Oops, wrong. Like so, okay? Just like these hyperbola, right? There are asymptotes. What are the asymptotes in this case? They're x equals 0 and y equals 0, okay? Now, we've kind of been looking at this guy and assuming him for a long time, but he's special because his asymptotes are perpendicular to each other. You know the very first one I gave you? What were the asymptotes? Do you remember what they were? I think it was like root 3x and minus root 3. There's something thereabouts, okay? They're not meeting at right angles, okay? So if I have them meeting at right angles, we call this one, and any variation of that kind, so long as the asymptotes are perpendicular, we call it the rectangular hyperbola. Because you know, a rectangle is the shape that has right angles in it. Okay. Now, here's a task for you to go and have a think about. What's the eccentricity of this thing? Every rectangular hyperbola has the same eccentricity. Do you believe me? But what is it, and how do you show it? You can get the answer. It's a very nice, neat number. But why is that? Why do they all have the same one? Any which way you turn it, it's still the same.